Yes, so my name is Heloise Meheut, and I'm an astronomer. I'm working on planet formation, and today I'd like to introduce you to some concept related to protoplanetary disks, so the region where planets form, and how it can be related to some of the tools or concepts you've seen in these programs. So we'll discuss wave instability and transport, especially of angular momentum and dust in protoplanetary disks. These disks indeed are formed a byproduct of star formation. They are formed just after the formation of the star, and they are quite thin, as we can see here. So these disks are in equilibrium between gravity force and centrifugal force. That's the reason why they are in Keplerian rotation. And indeed, in the radial direction, I don't know if you see my mouse, but the pressure gradient is quite negligible. That's why it's very close to Keplerian rotation. And all the dynamics of the disk is based on this rotation. So these disks are radially in rotation, and there is a shear in the radial direction, and they're also stratified radially. And in the vertical direction, it's an equilibrium, it's a standard hydrostatic equilibrium between gravity, the vertical component of the gravity of the star, and pressure force. And in this vertical direction, they are also stratified, and there is also some shear. At the first, as they are seen, if we look at large scale, these disks are often considered as being 2D, where the quantity are integrated vertically. And in 2D, at large scale, the pressure gradient and indeed the sound speed cannot be, has an important effect, so it's compressible. On small scale, so scale smaller than the scale height, the disk is should be considered as 3D, and there are a lot more 3D effects that we have to consider, as we'll see just after. But as a first approximation, we can consider the disk 2D. So the density is given here. It's just Gaussian, assuming there is the disk is isothermal vertically, and we can integrate the density, giving the surface density in the vertical direction that we will use just after. Just to give some numbers, the typical Mach number is quite high, and indeed we are more used to use this H here, which is the adimensional scale height of the disk. It's indeed the inverse of the Mach number. So it's a scale height, H, divided by the radius towards the star. So it's the aspect ratio of the disk. And typically it's 10 to the minus 2 to 10 to the minus 1. So the Mach number of Keplerian rotation is 10 to 100. The Rossby number is fixed by the gravity law. So it's given here. And typical Reynolds number, as defined here, is at least 10 to the 11 or 10 to the 14th. So this seems very high Reynolds number, but one of the main difficulty we have is to find a path to turbulence, despite this very high Reynolds number of Keplerian rotation. As I will explain just after. Since a few years, it's now possible to detect more and more structures in these disks, protoplanetary disk, and we have several observables that are useful to understand planet formation and to understand wave propagating in these disks. So typically we can observe them in millimeter wavelengths. So it's useful to detect millimeter-sized particles, dust, that are mainly in the mid-plane, as plotted here. But also at these wavelengths, we can look at the gas with line emission to detect, thanks to Doppler effect, to detect the dynamics inside this disk. And also they are observed in infrared or near or mid infrared, where we can see micrometer size dust. So that are all over vertically, all over the disk, as well as some also line emission. And finally, there is what we can see in the UV or near UV continuum. It's the accretion of the gas onto the star. And this accretion shows that there is transport through the disk, transport of mass, and therefore it means that there is transport of angular momentum. As you can see here, that there are several scales corresponding to several time scales. The typical dynamical time scale, Keplerian time scale around the star, is a few days close to the star, 1 year at 1 AU for a star like the Sun, and tens of years at the outer edge of the disk, that is several hundreds of astronomical units. So, as I said, to understand the evolution of this disk, we have to understand the angular momentum transport. And we know they are because we see the accretion onto the star, and also because we see that protoplanetary disks have a typical lifetime of a few million years. And after that, stars that are older than a few million years don't have protoplanetary disks. So it means that there is an evolution, and to explain this evolution, we need to understand angular momentum transport. So the first idea could be molecular viscosity, but indeed it's very low. As I said, the Reynolds number is very high, and the typical viscous time scale is 10 to the 11 year. So this cannot do the job. And other possibilities are hydroturbulence, MHD turbulence, but also outflows. So in hydroturbulence was a lot studied initially because, as I said, the Reynolds number is very high, but we have to fight against the stability effect of Keplerian rotation and shear to find a path to turbulence. And we can see it, for instance, in the Rayleigh stability criterion, which is shown here. So where R is a radius, omega is a rotation frequency. And this is strongly stabilizing. Then there was many studies on MHD turbulence, and especially magnetorotational instability, MRI, which is now not thought to be a perfect solution because of the low ionization fraction of this disk. And to have MHD active to transport, you need to have good coupling between the gas and the magnetic field, and so ionized gas. And the last solution is outflows, which is also related to magnetic fields. As this program is mainly on hydro, I will mainly discuss the hydroturbulence here, and some on the idea for explaining the hydroturbulence. Just to give you some equations that to explain what I've just said. If I write the conservation of mass here, you can see, so sigma again is the surface density, and what's written in red is correspond to the radial stress, so the transport in the radial direction, and in green is the vertical one. And so this is the first line is a conservation of mass, and the second line is a conservation of angular momentum. And in blue, it's correspond to the accretion process. If we are just at the limit of the star, it's the accretion onto the star. And we have separated the hydro part and the stress due to the magnetic field in both cases. And one of the main difficulties to find where these stresses could come from. What is the path to a turbulent state to have such turbulent stresses? There are several ideas that are discussed to find a path and to fight against this stability criterion and the stabilizing effect of Keplerian rotation. And there are now several hydrodynamic instabilities that are discussed. So I will just mention a few. Do not hesitate to go look at the paper for more details. But as I said, these disks are vertically sheared, and we can extract energy thanks to this vertical shear. This is the base of the vertical shear instability. There's also the entropy gradients that could help. And here this is the base of this time of the convective overstability. And the last one, which is is studied a lot, is zombie vortex instability since a few years too, where there you have baroclinic critical layers inside the disk. The one I want to discuss a bit more here is the Rossby wave instability, where you need to have potential vorticity gradients, PV gradients, as it's really directly related, I think, to what you've already seen here. And if I have time, I say a few words on the streaming instability. So the Rossby wave instability is an instability that grows if there is an extremum in potential vorticity that is defined here. So potential vorticity can be written also as a ratio between epicyclic frequency square, kappa, and here omega is the rotation rate and sigma again the density. So for instance, if you have an extremum in density, it could be unstable. And also if you are a disk this time around black hole, you could have an extremum in epicyclic frequency. But in protoplanetary disk, it's mainly an extremum in density that we can consider. And if there is such an extremum, like here, you have two gradients, meaning that you can have two Rossby waves, one in each gradient. If they have the same frequency, they can exchange energy, and indeed they would have the same frequencies that the fluid at the extremum of potential vorticity. So this is the kind of critical layer. And these two waves exchange energy, and one have frequency that is lower than the local fluid frequency, the Doppler shifted frequency. So we say it has a negative energy compared to the flow, and the other one has a higher frequency, so it has positive energy compared to the flow. And the exchange on energy allows the growth of the instability. On top of that, as we are in the Keplerian rotation disk, and as I said, compressibility is important at large scale. There are density waves propagating inward to the star and outward. But it's a loss of energy for the instability, and that will change obviously the growth rate of this instability. And we can see that we can write indeed the propagation of this wave, so the wave propagation equation in a potential that can be computed. And you see here two examples of potential in which this wave could propagate, depending on the azimuthal mode number of this wave, here, 2 and 5. And you see that there's two regions where the potential is negative, where the wave can propagate. So in the region of the extremum, here where you have the two Rossby wave, and also inward where you have a spiral density wave, and outward. And depending on the mode number, the width of the forbidden region change a loss of energy through this forbidden region. As you can see here, the smaller the mode number, the larger is the forbidden region. And so the higher is the growth rate. And indeed, this instability is a large-scale instability. So it's mainly 2D. And the nonlinear evolution would be an inverse cascade toward large scale, and there would be only one vortex surviving at the end. And this is really interesting in the context of planet formation, because one large-scale vortex could help to form planetesimals. Indeed, to understand planet formation, we have to understand the growth of solids from submicron size dust toward the size of a planet. The first steps are quite unknown. It's thanks to collision. The last one is gravity that helps. But the intermediate size solids, so to go from pebbles to planetesimals, is not very well known, and probably it's a coupling between the solids and the gas that would allow us to form planetesimals. And if we have one large-scale anticyclone, like the one formed by the Rossby wave instabilities, it could help to concentrate solids at the center of these anticyclones, and where you could have local gravitational collapse and formation of planetesimals. So that's another big question of the domain. That's how to concentrate the dust in order to form planetesimals. Depending on the size of the dust, so the Stokes corresponding to different Stokes number, you have different processes to concentrate solids. The one we are the most interested in are the pebbles to form planetesimals that have Stokes number of the order of 1 about. And so ideas that are discussed are pressure bump, large-scale vortices, but also the streaming instability, which is which can grow when we consider the solids as active particles. So we include the back reaction of the solids onto the gas, as shown in the equation below. And in this case, there is an unstable process because the solids tend to slow down the gas that again tend to concentrate the solids. And we have higher and higher density, and maybe a density high enough to have a gravitational collapse. So this was a very, very quick introduction to protoplanetary disk and some of the open questions we have in this domain. I don't have so much time to go into details, but so I will explain here just some of the main questions I already discussed. But if you have tools or ideas that you have developed in another domain that could help to answer some of these questions, I think it would be very interesting. So that's what drives the evolution of the protoplanetary disk and how the planetesimals are formed, and is there a coupling between these two processes? And the last I didn't discuss, I didn't have so much time, but is also how to explain the structures that are now detected in protoplanetary disk, as the one you can see below. You can see that now we detect spirals, we detect also crescent shapes, a lot of ring shapes, and these structures are seen in micron-sized dust and millimeter dust. So this means that there is transport of these solids in this disk, and we need to understand the process that can explain this transport. Okay, thank you. I'll stop here.
Thank you, Heloise. Thank you for this very nice introduction to protoplanetary disk. Are there any questions? We have at least 1 minute. I have at least one quick, Heloise. You explained to us that you are expecting at the end only one single large-scale vortex. If you have, if you are looking for dust repartition with only one vortex, where do we expect the dust to go?
At the center of the anticyclone. And indeed, structures like this one, the question here, can be interpreted as one large-scale anticyclone here that tend to concentrate the solids at the center, the solids, the millimeter-sized solids, at the, which has Stokes number of the other one, at the center of the anticyclone. And indeed, this is the same disk. This is the same disk observed here in millimeter and here in micron waves, micron size wave. And so here we see lots smaller dust, which has Stokes number a lot smaller. So that's more tend to follow the gas. And you don't see such concentration. So that's also why it can be interpreted as a vortex.
And with respect to the potentials you showed us in one of the slides, there are some forbidden gaps. Do you expect some tunnel effect? Do you expect tunneling effect?
Yeah, exactly. That's a tunneling effect through this forbidden region. And that's why you can have Rossby wave inside this in the extremum of close to the extremum of potential vorticity, tunneling effect, and then a spiral density wave in the inner region, but also in the outer region.
And the last question from the chat from Anubhab: are collisions between dust particles important in the formation of the protoplanetary disk?
Yeah, it's important for the formation of planetesimals, and indeed that's one of the questions, one of the problem from formation of planetesimals, because the collision of pebbles tend to be destructive and not allow the growth. So it's another process to be studied.
Okay, thank you very much, Heloise.